Math372, Complex Analysis, Lecture 27. So today we're going to do Laplace's method. So I have written down some conditions here. These are not the most general. When I give the proof, I'm not going to give the most general as well. There is a whole class you can give on methods like this. There's a lot of stuff in the appendix. What I want to do is I want to do enough to give you a sense of what kind of techniques are out there. I want to show you ways to approximate things. And I want to show you how different levels of approximation give you different types of results. Depending on how much work you do, you can do a better job getting the constants. So what we're going to do here is I'm going to assume phi and c are infinitely differentiable functions. I almost surely do not need infinitely differentiable. Probably 3, 4 derivatives is more than enough. I'll assume that they're real valued. I will assume that phi of x naught equals phi prime of x naught equals 0. Well, the phi of x naught equaling 0, that's not so bad. That's just a shift. The phi prime of x naught, assuming that there's a place where it vanishes, that's more important. And we're going to assume that phi double prime of x is always greater than 0 in the interval ab, and the point x naught will be in that interval. So what is this going to mean? So one of the reasons I was mumbling the Asimov poetry is he's talking about how a kid thinks he's extremely old because he was 55 years old. And he talks about how his ancestors throughout time have been reading the works of Asimov. And Asimov gets frustrated with this little kid and kills him. How many of you have seen stuff like this? Function prime, function double prime in terms of curve sketching. So you've seen stuff like this?
Yeah, like
Calc 1. So for instance, let's say I have a point x naught where the first derivative is 0. And then I tell you that f double prime is greater than 0 in my interval. What can you now say about f prime knowing this about f double prime? F prime is increasing. So if f is 0 here and it's increasing, f prime must be positive in here. If f is increasing and it's 0 here, what must be true about f prime here? It must be negative. Now that I know my function looks like this, when I do my plot, I know x naught has to be a minimum. My function goes down and then comes up. Exactly how it does that, I don't know. But this is the power of curve sketching, is we now have a rough sense of what our function looks like when I tell you, the first derivative vanishes at a point, and the second derivative is positive in this interval. So this is basically going back to the first and the second derivative tests. Okay. If this was a 400 level class, I would be saying, well, this is a senior seminar. I'm supposed to tie everything back together. Let's go all the way back to Calc 1 and curve sketching. But it's amazing how much information we get when we're told, phi double prime is greater than 0 and phi prime. And then it says that this integral is equal to the following with a small error term. So you were looking at what's going on as s goes to infinity. And so for the most part, we'll take s maybe being real valued. And if you look at this, this term is 1 over square root of s smaller than this term. So as s gets very, very large, this is negligible relative to this. For a lot of applications, we only care about the main term. If we are trying to estimate n factorial, which we will, we often want to figure out, well, let's say the sum x to the n over n factorial, the e to the x, does this converge for all x? We don't really care about the error term in n factorial. We care about the main term in n factorial. Oftentimes, in more delicate applications, you subtract off the main term and you care about those lower fluctuations. When you look at this, any number in A look interesting to you? So this is pattern detection now. Square root of 2 pi. Where have you seen square root of 2 pi before?
Something we did on Monday.
Okay, which is? It has at least 3 names. This distribution has at least 3 names. The Gaussian, the normal, the bell curve. We've seen square root of 2 pi as the normalization constant of a Gaussian. Is this suggestive that there is a normal distribution lurking in the background? So again, one of the things I really want to highlight is just how you look at problems like this. I'm going to first give you the poor mathematician's Stirling's formula. So we want to approximate n factorial. And that's going to be our goal today, is to apply this to understand the size of n factorial. What's the first thing you should do when you see n factorial? You should be having a Pavlovian response. You should be trying hard to resist doing this, but you can't. You have to. You have to take a log. Right? Whenever you see a product in mathematics now, I want you to always be thinking of logs. Okay? If you study the log of n factorial, this is now the sum, k goes from 1 to n, of the log of k. And if you plot this, it's going to look something like this. And then what we'll do is we do the integral test. And you can get your lower approximations to it. You can get your upper approximations to it. And then this sum will be sandwiched in between. So I'm not going to go through the details, but this should basically be like the integral from 1 to n of log of t dt. Again, do the details. We need an antiderivative log of t. It's t log t minus t. One way you can see that, well, if I have a t log t, if I take the derivative, when I take the derivative here, I'm going to get a log t. And then when I take the derivative here, I'm going to get a 1 over t, so I'm going to get an extra 1. I have to cancel. So sometimes if you guess the form of the derivative, if you're a little bit off, you can figure it out and tweak it. So then you could try, well, could I figure out what the antiderivative log squared, log cubed, log to the k? Is that something I could do? What if I had t squared log t? Could I find an antiderivative for that? I evaluate this at 1 and n. So I should get n log n minus n. And then when I put in 1, I'll get 1 log 1. Right, that doesn't really matter. And then get a minus 1. So then that means n factorial should be about e to the n log n minus 1. Well, e to the log n is just n. So this is n to the n, e to the minus n, and then a 1 over e. Not bad. So, just by using the integral test, not so bad. Now, this is supposed to be not a 1 over e, but a square root of 2 pi n. If you look at the integral test and what we're doing, really the error comes down to the first box and the last box. And so in a lot of these things, you have this fact of 1/2 of those things. You get a 1/2 log n. Ooh, when you exponentiate 1/2 log n, what do you get? So if you exponentiate 1/2 log n, what is that? Square root of n. And that would actually get you a little bit better. So if you do a little bit more work with the integral test, if you look at some of the like Euler summation formulas, you can actually see that it's looking like a square root of n over there. But without too much work, you get a pretty good sense. And you'd get a lower bound like this. You'd get an upper bound with an n. Take the geometric mean. That's often something you do in these cases, or the averaging over here. And that's the square root of n. You're not going to get the constant 2 pi. But you'll be getting that's going to look like square root of n. All right, so this is one. Oh, good, it is turning today. It's a good day. So this is one approach. Let's look at another approach. Gamma of n plus 1 is n factorial. This is going to be the integral from 0 to infinity of e to the minus n x, e to the minus x, x to the n dx. Okay, so this is my integrand. Let's call this f of x. What happens as x goes to 0? What happens to the integrand? Goes to 0. What happens as x goes to infinity? Goes to 0. Good, so this has at least a chance of being integrable. You've got exponential decay, good. You've got polynomial death, that's good. Okay, everything's fine. If you calculate the derivative, you get a lot of information. So f prime of x is going to be negative e to the negative x, x to the n, plus e to the x, and x to the n minus 1. So if I factor, I get e to the negative x, x to the n, then I'll have negative x plus n. So what this tells you is here is n, here's f prime. If x is less than n, it's positive. If x is greater than n, it's negative. So when I plot my function f, it has a maximum at n. This is the curve sketching day. What is that maximum value? Well, f of n is e to the minus n, n to the n. So as a rough guess, maybe n factorial is about e to the minus n, n to the n. This is a lot less rigorous. But it's sometimes nice to have a rough ballpark feeling of what something should be. The question, of course, is, well, how far can x go without having the integrand change significantly? Can I go as far as square root of x? Can I go as far as log x? How far of a window do I have where this value is approximately constant? So it's a nice exercise. Try to see how far you can push this. We know this is the largest value. Once x gets sufficiently large, we should have enough extra decay from the exponential or from in the other direction from this that we should be OK. So try to make that precise. OK, so these were just two rough sketches of things to try. Let's look at this now. So we want to prove Laplace's formula, or the Laplace method. For a lot of these things, sometimes it's easier to just do it ad hoc for whatever you're looking at than always remembering the exact conditions and whatnot. All right, so we have a bunch of things over here. So I've written down 5 steps. I'm going to try to follow my notes. Step 1, let's assume phi of x naught equals 0. So actually, over here, I guess I'm not assuming phi of x naught is 0, because I'm actually writing it with a phi of x naught over here. If phi of x naught is not equal to 0, well, all I have to do is subtract phi of x naught, add phi of x naught, and then I would just pull out an e to the s, negative s, phi of x naught. So it really doesn't hurt me that much to assume phi of x naught is 0. With a little bit of work, you could almost even translate x and make x equal to 0 if you want. Sometimes it's more convenient not to have x equals 0 the way things are defined. But this is fine. If not, you just look at phi of x minus phi of x naught plus phi of x naught. And then that's our new function. We just pull the other thing out. All right, so that's step 1. So step 2 is going to be a Taylor series expansion. So what we want to do is we want to look at phi of x. We now know that phi of x naught is 0. Phi prime of x naught is 0. So this means phi of x has to look like phi double prime of x naught, x minus x naught squared with the 1/2. I'm trying to think, did I actually remember to put in the 1/2? Oh, I did remember to put in the half. Good, excellent. And now what comes next? So I'm expanding phi about the point x naught. Because phi of x naught is 0 and because phi prime of x naught is 0, the first 2 terms in the Taylor series expansion aren't present. So the first term that's present is this. What about what comes next?
I'm sorry, but what is the goal of what we're doing right now? Are we still trying to estimate n factorial?
Well, we're going to then use this for n factorial. This is a general statement. If I have 2 functions phi and c, then here's a way to approximate this integral.
Okay.
And then we will apply it, and you can begin to see that this should look a lot like maybe the n factorial.
Okay.
Maybe this would be like an x.
Yeah. So that equation right now is what we're proving.
Right now we're trying to prove this. We're trying to prove Laplace's method, and then we'll apply it to n factorial. So what we're doing here is we're doing a Taylor expansion of phi of x. And so because the first 2 things vanish, it looks like this. What about the next term? And this is where you need to assume some things about the function if you want the expansion to exist and the expansion to be nice. And so this is where it gets a little bit complicated. If I assume my function is analytic, then I can keep writing down the Taylor series expansion. If I assume the function is at least 3 or 4 times differentiable, I can then write down maybe the third derivative at a point with an x minus x naught cubed or something like that. So it comes down to what do you want to assume about the function. So what I'm going to assume, and I think I'm going to write it in this way, as I'm going to multiply it by 1 plus phi of x.
So it's just like the less differentiable it is, the less accurately you can.
Well, no, the less I'll know about this function phi.
And thus the less accurately you can estimate it? Or
Not necessarily the less accurately, it's going to affect the structure of what phi is. Now, for the most part, I don't really care that much about phi because it's going to be a lower order term. And so the question is always going to be, how do we want to write this? I'm just trying to make sure that this is consistent with the notes I gave you. I'm going to just write it. I'll write it a little bit differently. OK, so I guess I'm writing it differently. So I'm writing it like this, with a phi of x like this. So if you have a Taylor series expansion, we know it has to start like this. And we know phi double prime is not 0. And then we would have all the other terms. And so what this would mean is phi of x would have to equal 1 plus something of size x minus x naught. Because we want something small. And so this one over here gives us our first term. Then the next term would have an x minus x naught cubed, then an x minus x naught to the fourth, and an x minus x naught to the fifth. If I had my function was analytic, I could write down something like that, and I would have a really nice formula for phi. It would be an infinite sum. But maybe my function is not infinitely differentiable. Maybe my function is only differentiable 3 or 4 times. But as long as it's differentiable 3 or 4 times, I would have something like this over here. I wouldn't necessarily know exactly the form of this. Maybe it's not a nice form. But it's a much smaller term. And so as long as x is close to x naught, this part here is much, much smaller. Because it's x minus x naught cubed when it hits this. Whereas this is giving us an x minus x naught squared. You always want to get a sense of the size of things. If you look at this, we have negative s phi of x. We have negative s phi of x. Let's think about what's going on. The smallest value of phi is at x naught. So we the smallest value or the largest value? Smallest value. And so for us, we'll think maybe s is going to infinity. So s is positive. This is in the exponential. The larger phi of x is, the smaller the contribution. Right? So look at it this way. We have this term here. Let's say phi of x naught is 5. So no matter what, we always have an e to the, oh God, with an s, 5 is terrible. Sorry. Let's make it 17. 17 is my son's favorite number right now. So we have e to the negative 17s. No matter what, you can't be larger than that. But the larger phi of x naught gets, the smaller the contribution is going to be. And so the smallest value of phi of x naught, so the smallest value of phi of x is at x naught. The more we move away from x naught, the smaller this contribution will eventually be. Well, how much smaller? We're assuming, just to make things easy, that phi of x naught is 0. OK, I can understand e to the negative 0. That's very nice. That's a contribution of 1. Now let's say we move so that phi of x is now 1/10. We have e to the negative s over 10. And s is going to infinity. So, phi of x naught is 0. Let's say phi of x1, let's do 1 over 10 to the 10. Let's be excessive. E to the negative s phi of x naught, what is that equal to? 1. Does it matter how large s is? No. Let's look at this. E to the negative s phi of x1, this is e to the negative s over 10 to the 10. is this large or small? It goes to 0, right? Why does it go to 0?
Well, because S goes to infinity.
Because S goes to infinity. So eventually, it is going to be a, I'm going to just try it and see if I shake this if it works. Eventually, it's going to give us a negligible contribution. Because S goes to infinity, once S is really, really large, this is small. Now, moving 1 over 10 to the 10th from 0 is not a large movement. But as S goes to infinity, the contribution is negligibly smaller. So essentially, all the contribution is in a really small band. And then the question becomes, how small of a band? Well, the band, it seems to make sense, should depend on the size of S. So if I look at something like this, if I move this value by 1 over S, so now let's assume phi of x1 was 1 over S. Then in this case, I would get negative S over S. And this is 1 over E. Is 1 over E large or small? Or how is this relative to 1? It's a little bit smaller. It's comparable. Right? It's only about 30% the size. Or 37%. It's order of magnitude, it's the same. So if I've moved over just 1 over S, the contribution is still significant. I can't ignore the contribution when phi of x1 is of size 1 over S. That's still going to contribute. Okay? What if I moved all the way so that now phi of S1 was 1 over square root of S? Now I would get e to the negative square root of S. This is known as damn small. Okay? As S goes to infinity, this is magnitudes less than 1. You then just have to show that even when you integrate, it's going to be fine. Well, this has enough decay, I'm not that worried. Now, of course, we then have to integrate phi, but as long as C has a fine integral, we see that if we move over just a little bit on the scale of 1 over square root of S, already this exponential is going to be so much smaller, we're not going to have to worry about things. This should hopefully give you some sense of, well, maybe this does look reasonable. A 1 over S versus a 1 over square root of S. Of course, I could have done the same argument. I could have moved 1 over S to the 3/4. I could have moved over 1 over S to the 1/4. They would all give me a positive power of S up here. So it's not clear exactly how far I should be able to move, but it does look like if I move over 1 over square root of S, that should be enough that the contribution is so small that it doesn't really matter. And then the hope is, well, if S is really large, if phi is nice for x to move so that this is changing by like 1 over square root of S, x can't move that much. If x can't move that much, what's happening to C? How much can C change by? Not much. If x is only moving on the order, if I want this to change by like a 1 over square root of S, x can't move by much by continuity. So this value can't change by that much. So I should almost be able to approximate maybe by a constant or something like that and get some sense of what's going on. So I really care more about the ideas behind the method, the ideas about how you look at something like this, than the nuts and bolts of applying this. But you want to get a feel for where's the contribution. That's why over there, that part that was erased, when we did the n factorial, we said, well, let's look where the integrand is largest. It's largest when x equals n, so let's just approximate it by n to the n e to the minus n. Then the question is just, over what window is that? And we do know that it's changing. We saw that it changed by a 1 over e. So how do we take into account those changes? It's suggesting that there's maybe a Gaussian going on. Okay, so this is step 2, is that what we want to do here is we want to replace our function. Our function, little phi, related to big phi, is going to be 1 at the point x0. And then as we move over a very small amount by continuity, it's not going to change that much. Yep?
Is it suggesting there's a Gaussian going on because there's rapid decay? Or
Not rapid decay. What's suggesting the Gaussian is we have this as something squared. And when you put that in here, that's where the Gaussian is coming from. So if you now substitute that in, so we're now moving on to step 3. And now it's moving. So if we put this in, we have an e to the negative s. And now I'm going to have a 1/2 phi of x naught, x minus x naught squared, 1 plus an error term of size x minus x naught. This over here is looking like a Gaussian. I want to have e to the negative y squared over 2 sigma squared. So it looks like there's a couple of ways of doing this. We can choose, do we want to put this in the variance or not? This is clearly going to be somehow related to the y. So this is my like x minus x naught. And so if I'm doing it like this, then I would have to have 1 over sigma squared is phi of x naught and an s. So the variance is looking like 1 over the square root of s phi of x naught. Oh, and this is, I think, the second derivative. That's not going to be visible in the camera. So it's looking like a Gaussian with variance 1 over square root of s phi double prime x naught. What can you tell me about this variance as s goes to infinity? It's going to 0. So as s goes to infinity, sigma goes to 0. So this is looking like a more and more peaked Gaussian. Gaussians have rapid decay, right? So we've got a Gaussian with extremely rapid decay. So essentially all the mass is concentrated at x naught. We know how to integrate a Gaussian, right? When you integrate a Gaussian, you want to multiply by 1 over square root of 2 pi sigma squared. Well, we don't have that. So we have to multiply by 1. So now if you look what happens, this should integrate to 1. And we're left with a square root of 2 pi sigma squared. So we're left with this piece here, which is a square root of 2 pi, and then sigma squared would be a 1 over s phi double prime of x naught. But we have to take the, we have to take the square root of that. So now we have the square root of this. And if you look at what we have for a, if we go all the way back, oh good, it's turning. There's the square root of 2 pi. There's the square root of phi double prime of x naught in the denominator. There's the 1 over square root of s. Everything works. The only thing that we have now is the c of x naught. Well, that's just because the integration is over such a small range of x that we can essentially just approximate this by c of x naught. And so now what I'm hoping you're seeing is where the Gaussian is coming from. It's coming from the fact that because the first derivative vanishes and because s is going to infinity, essentially all the contribution is coming near x naught. And in that case, the exponent looks like that of a Gaussian. So now it all comes down to the bookkeeping. And so the book goes through one method. In the notes that I've posted, I go through another set in terms of just how explicitly do you want to do this calculation.
Sorry.
Yes, no, please.
The term on the right, was that the 1 over
Which
sigma
one?
squared, was that being multiplied by the
This over here?
Yeah.
This is just saying, how do we calculate, this is looking like a Gaussian.
Yeah, okay, so that was a part of it. The thing on the left,
Right here?
that goes to 1.
The integral of this goes to 1.
Yeah. So where is that other square root coming
Oh, it's just, what is the square root of 2 pi sigma squared?
Oh, you just broke. Oh. Okay.
Right? So this integrates to 1.
Yeah, I'm good.
Yep. And so over here, this is just saying that our answer is looking really, really reasonable. Okay? And then we just have to figure out how do we deal with stuff like this. So there's lots of different ways of doing the analysis here. I am trying to do a way that gives you a sense of what's going on without overwhelming you with all the calculations and error analysis and error estimation. But close enough that if you want to put in the details, if you want to read the book carefully, you have enough so that you can follow it. Speaking of following, let's see if it will follow. No, thank you. Excellent. So let's look a little bit as to what's going on. So I'm going to see if I can do this without doing all the painful change of variables. So we have the integral from a to b of blah. Okay? And x naught lives somewhere in that range. Okay? So this is like the integral of x naught minus, say, alpha to x naught plus beta. And I'll put a little s over here to tell us this depends on s. Plus the integral over the rest. And the idea is, as long as these are somewhat reasonable, in this place over here, the exponential decay from this is so large that the contribution of this doesn't matter. So this is always a question as to how much detail do you want to get into on the board. And so you can go through, you can read all the algebra. My notes are actually, I think, pretty good in terms of going through all the steps. I want to give you the high point. So here, as long as alpha of s and beta of s are somewhat reasonable, we're going to have so much decay here that we're fine. We could probably take maybe alpha of s to equal beta of s to equal maybe like 1 over square root of s. And if we go that far, is that enough? Well, when we were looking at things, if we now have this moving over a 1 over square root of s, are we happy with that, or do we want to move a little bit further? So we've got a x minus x naught. So if we're moving maybe on the order of 1 over square root of s, if we square that, oh crap. That's going to be of size 1 over s. That perfectly cancels the s over here. So if we move 1 over square root of s, we might not have moved just far enough. It's trying to get a sense of how far do you need to move. If x is moving only 1 over square root of s away from x naught, this quantity over here is going to look like 1 over s. 1 over s times s is going to be of size 1. So moving 1 over square root of s is not enough. We need to move a little bit more. If we move maybe 1 over s to the 1/4, or 1 over s log s, something like that would be enough. If you think about what's going on, what is the standard deviation? The standard deviation is of size 1 over square root of s. So if you have a Gaussian, if you move over one standard deviation, you still have a reasonable probability. Once you move over a large number of standard deviations, so anybody know the probability of being 10 standard deviations away from the mean? Almost zero. And so if somebody has Mathematica and wants to just quickly open up and just see how unlikely that is. It is, I probably should have looked it up, but it is so unlikely to be 10 standard deviations away that it just, did you get it? Or?
I don't know where.
Oh, okay. I will do it quickly as I talk. To be 10 standard deviations away is negligible. If you know probability, if you know Chebyshev's bound, it's at most 1 over the number of standard deviations squared. So that gives you a 1 over 100. But the probability is significantly less than 1 over 100. And so, all right, so I will do numerical integrate 2 divided by square root of 2 pi, and then I want to integrate my computer has just frozen. All right, there we go. All right, then we want exponential negative x squared over 2 x goes from 10 to infinity. And so it is approximately 10 to the negative 23. Okay, so when we're talking small, we do mean small. Now what I love is Chebyshev's bound only gives you 1 over 100. The actual answer is around 10 to the negative 23. 10 to the negative 23, however, is still a large number relative to s. It's a fixed positive number. We don't have any s decay. It's not going to 0. So if we are only moving over 1 over square root of s, that's not enough to have this become negligible. You want to move over some number of standard deviations that's a function of s. If I move over log s standard deviations, if I move over s to the 1/4 standard deviations, then the Gaussian is going to have a decay in s. And then that will go to 0, and then that will be negligible. So over here, if I wanted to just choose alpha and beta naively to just be 1 over square root of s, it's just not quite enough. So I want to do a little bit more. And so as long as I have something like this, the integral over the rest, this now basically just goes to 0 as s goes to infinity. And now we're left with integrating this over a small region. Okay? And now in that region, it is looking a lot like a Gaussian. And because we're going over so many standard deviations, we've gone over so many standard deviations that it's essentially the same as integrating from minus infinity to infinity. So we then say that the integral from x0 minus alpha s to x0 plus beta s is roughly the same as integrating from minus infinity to infinity. Because once you've gone log s or s to the 1/4 standard deviations, you've got all the mass of the Gaussian. We have to be slightly careful because order matters. So over here, remember, we don't have a pure Gaussian, right? Thank you. It's not. Thank you. So right now, we don't have a pure Gaussian. We have this x minus x0 term. So what we first have to do is we have to see what is the contribution of this in that interval that we care about. Show that we can remove that, and then we can extend to infinity. So we first, so it moves back, so it's order matters for this. It can move in this direction, but not that direction. So before do this, first we deal with the order x minus x0 piece. Okay? And the question becomes, how much of a contribution can this x minus x0 piece give us? Well, we can just write this as it's going to be an e to the negative s 1/2 phi double prime of x0, and then something of size x minus x0 cubed. So the question is, do we expect this to be that large?
As gets large, doesn't it get really, really small?
So that's one of the problems.
Oh, yeah. Okay.
Right? So we need to make sure that this is sufficient so that we want this exponent to be something like 0.
How can that be sufficient if that's directly a function of how far you're moving?
Well, if we haven't moved that far, then we can have the denominator maybe like 1 over s to the 5th. And if the denominator is like 1 over s to the 5th, then we have an s up top. Oh, that's 1 over s to the 4th. That's clearly going to be small. That'll look like e to the 0, and it will be negligible. So roughly, how large can x minus x0 be? If it's like s to the 1/3, if it's like 1 over s to the 1/3, then even when I cube it, it's not going to be too bad. So if I had x minus x0 roughly of size, say, 1 over s to the 1/3 plus epsilon, then when I cube this, I'll have a little bit smaller than 1 over s. I'll have a 1 over s to the 1 plus 3 epsilon. I have an s over here, so this would look like a 1 over s to the epsilon. So if we are only going up to on the size of s to the 1/3, we're okay. In terms of the contribution from that piece. Unfortunately, how large did we say x minus x naught had to be? We were like 1 over s to the 1/4. If we tried something like 1 over square root of s, that was going too far. So this is where you have to be a little bit more careful in terms of what goes on. This is the last painful step, is we can't move too far, or if we move too far, then that piece is becoming negligible. Well, what's the contribution from that piece? So let's see, are we okay or are we in trouble? So we have two different competing influences. I'm going to kill this now. The error piece is okay if x minus x naught is less equal to 1 over s to the 1/3 plus epsilon. We wanted to take alpha and beta to be like 1 over s to the 1/4. Could we have taken 1 over s to the 1/3? Would that have been okay? We just couldn't go so before we took alpha s equals beta s equals 1 over s to the 1/4. Why didn't we take 1 over square root of s? We got a 1 over s. Could we have done 1 over s to the 1/3? Yeah, that would have been fine. So all we need to do is we were trying to decide how far can we push this. We just have to change how far we push that. It will still be okay in this piece. So just change alpha s, beta s to be 1 over s to the 1/3 plus epsilon. So we saw 1 over square root of s was not going far enough. We need to go a little bit farther. 1 over s to the 1/4 is too far, but we can go 1 over s to the 1/3. And that's what you need now to make it rigorous. And then you can show this piece is small. We can now drop this piece because it's approximately 1. And now we can then, now that we've dropped it, now we have a nice Gaussian, and now we can extend that to infinity. So a really good exercise, I'm not really assigning homework on these problems, is to go through and make this rigorous. Is go through, drop all the pieces, show how small they are. And because x minus x naught is moving so little, then you will have, c of x naught is approximately c of x. There's really no change in the value because we moved so little. All right, so for the last minute, I guess we got 5 minutes, I want to just quickly do n factorial. So we can either do gamma of n plus 1 or gamma of n. Doesn't really matter. Gamma of n plus 1 is n factorial. I'm going to look at gamma of n is the integral from 0 to infinity of e to the negative x, x to the n, dx over x. And we're going to see today that it's actually nice to write it as dx over x after all of this stuff. Okay, well, more generally, gamma of s is the integral from 0 to infinity e to the negative x, x to the s, dx over x. This is the same as the integral from 0 to infinity, and this is all in my notes. Then I'll write this as x to the s is e to the negative, s log x dx over x. This is the same as the integral from 0 to infinity of e to the negative s negative log x minus x 1 over x dx. And this is going to be my function c of x. And that function is nice. It does blow up as x goes to 0, but it blows up in a very nice way. Now, notice that this is not the same form as this. I have s phi of x. Here I only have s times this part, and I don't have the s there. So we're going to change variables. We're going to send x to s times x. And now, finally, after all this talk about why we like to look at dx over x, the part dx over x doesn't change. And so what we will get is that this is equal to the integral from 0 to infinity e to the negative s negative log sx minus sx 1 over x dx. Well, I can use the log of a product as the sum of the logs. I will pull out an e to the s log s. I will then have an integral from 0 to infinity of e to the negative s x minus log x dx, if I've done it correctly. And I think I now need to do one small little change. I'm sorry? Oh, yeah, I have the 1 over x here. Thank you. OK. So what I want to do now is this is the same as e to the s log s minus s, integral from 0 to infinity, e to the negative s, x minus log of x minus 1 over x dx. So this will give me an e to the s, which cancels with that. The reason I'm doing this is now I want my phi of x to be x minus log x minus 1. Phi of 1 is 1 minus 0 minus 1 is 0. Phi double prime of 1, well, if I take phi prime of x, that's going to be 1 minus 1 over x. Phi double prime of 1 is 0. I'm sorry, phi prime of 1 is 0. Phi double prime of x is negative 1 over x squared when the negative becomes a positive, which is now going to be greater than 0. So all my conditions are satisfied. So I just put in this negative 1 so that phi of 1 was 0. And now I can apply the theorem as to what this integral should be. And so I should be getting e to the s log s minus s. And now I'll have a, which is a square root of 2 pi. I multiply by c of x naught. My point x naught is 1, so that's fine. That's just 1. And then I divide by the square root of phi double prime at 1. What's phi double prime at 1? 1. Everything is nice. And I have a square root of s. So this is the main term. So this is going to give us a, if we take s equals n, we get gamma of n is n to the n e to the minus n square root of 2 pi over n. So over square root of n. Gamma of n plus 1 is n gamma of n. This is n factorial. And now when I multiply by the n, the square root of n comes upstairs. And that gets us n to the n, e to the minus n, square root of 2 pi n. And there's Stirling's formula. There's the main term. There's the lower term. This is a really good place to stop. We just did it in the 50 minutes. The really quick recap is we have a general formula. We can now apply it. You often have to do a little bit of algebraic tweaks to make things work out. We finally saw why dx over x is so nice to work with. So there's a lot of good stuff for this. All right, we'll probably be shifting to probability for Friday.